image reconstruction from truncated data of a limited angle range in CT. Slightly different from the
Thank you, Rob. So Dan cannot be here. What happened? Dan cannot be here today, so I'm presenting for him, and I will try to answer questions if you guys have any question for him. So basically, this small story in which he investigated the image reconstruction from data, sort of collect from offset detector. You guys are the expert. Offset detectors widely used in mostly non-diagnostic applications, dental, C-arm, for the chest, etc. So there are some truncations, and not only that, we know that if you do full angular scan, you will be able to reconstruct pretty reasonably, and there's a solution for that kind of model in that case. You have offset detector under certain conditions, so you can solve it. You can do accurate reconstruction. That's what happened, in other products, in applications. But what he's going to look at is the data of offset detector over a limited angular range instead of full 2 pi angular range, for example. And so he developed a sort of DTV algorithm to reconstruct the image. I'm going to show that. So just put everything in the context. This is a image everybody probably is familiar with. Suppose you have a cone beam, fan beam. I don't know how to use it. Yeah. Then in the bottom, it's a data space. In the fan beam case, just I use this as an example. Your cone beam is saying arbitrary trajectory, fine. But so the horizontal axis is the sort of detector size, and vertical is the angle. So from 0 to 2 pi, and over the entire detector. That's the full detector, full angular range samples. So you see the database, data space looks like that. And to put it, the offset detector in context. In this case, the detector is not has the size that is smaller than the full detector, shown on the right-hand side. Yeah. And in terms of data you collected in this case is in the sonogram space on the right, and with the bright part, the gray part is sort of we suppress it, but you still have a sense how much data you're missing there. But anyway, this is not a big deal. People can do that. So what is interesting is look at the limited angle range of offset detector. So if you look at the space, data space, we'll look at those bright regions. One is a single arc of limited angle range, and the right ones has a double angle range, limited angle range arcs. In this case, he put it in the orthogonal directions. So the question is that is there a way we can do some kind of thing from this kind of data instead of the full data? So that's what is looking at. So the data model we're looking at is in essence still like actually transform, discrete form. We're not talking about the continuous. So the task here is to, the inverse problem here is to determine F from knowledge of G and H. Well, in full scan case, you have the full knowledge of H. H is a full blown matrix, and G is the full data set. And truncate, in the offset detect case, part of the H is missing. The data is missing as well. So in the limited angle range case, H is severely, sort of a change compared to the full blown case. All right, so that's the problem we're going to deal with. Of course, this is a discrete model that the matrix size is going to be sizable, a natural thing is optimization approach. You set up a matrix, surrogate matrix, which is your object function. You think that's if I can minimize or maximize that surrogate metric, then that's my solution. Whether it's useful or not, we worry about later. Whether it's solve the inverse problem or not, we worry about later. So that's how we set up the things. Everybody does this, or maybe there's a deep learning as well, but there is also some kind of loss function involved, training involved, etc. Anyway, so we're dealing with discrete model. You use an optimization approach. So here we have two terms, or two parts. One is the data fidelity part. G here is the model data. We call it, it's X-ray transform. F comes in there, and GM is the data you measure it. We worry about later what I mean by that. And you have constraint parts. We played, many of us played like image TV constraint, which is quite interesting. And here we look at the so-called direction of TV, along two orthogonal directions. You calculate the difference of the image, you calculate L1, norm of that, then you sum. So you constrain that. If you do a little bit analysis, you realize that this constraint is tighter than TV. So therefore, you're going to have a set specified by this object function that is tighter than, say, L2 itself, or the net of L2, or that of L2 plus TV. So that's the whole essence here. And for this kind of it's convex problem, you can derive. You have all kinds of algorithms and to solve it. And here we love this prime view thing. So we derive an instance algorithm from that approach to solve this problem. So this I already said that. Okay. So this is the algorithm, the pseudocode for the algorithm. I'm not going to get into details. It's very pretty much standard now. So basically you have an iterative algorithm. So we derive it, and most important, also important, equally important, it is for us. I feel it's important to define the convergency of the algorithm. You define how you solve the problem. So we need to answer that question. So that to answer that, there's no way you can do an analytical verification. You have to do numerical. So we have to set up the numerical study. Those are the parameters. This is the object function, the image function, which it's a real patient dental data, dental image. You see some artifacts. In our study, those artifacts are truth now. So anyway, and with that, we're going to do some kind of verification to say the algorithm we have can solve this object function. You have an object function, you claim you derive the algorithm solving that, then let's see if you can solve it. Actually, theoretically you can prove it solve this problem, but one thing is that when the iterative algorithm solve a DD model, actually there's no approximation. It's the implementation in terms of the implementation of the algorithm. In the computer code, it's exactly the same. So you have at least you have to verify your computer code is doing what you're saying are doing. So here we're going to do some numerical study to verify it, and for simplicity, we just say the measurement data in this verification study, it doesn't have to, but assume it's just the model data. We generate the simulation data that we plug in. So anyway, so we do the iteration, and we put together it's very relatively straightforward bunch of convergence matrix. For example, the second one is very straightforward. No, not the second one. Yeah, the bottom, the last one is very straightforward. The data divergence, data difference has to be almost zero when you converge. The horizontal line is the number of iterations, and you can see that they're all those metrics are converging to the single precision. So in this case, you don't worry about the iteration number as a parameter. It's to me, it's very important. Why do we have to derive a bunch of convergence conditions here? Well, the reason is that we feel that each one is only a necessary condition. So maybe you can derive a bunch of them. They all cover one aspect of the convergence properties, so it can be tight. So we're not quite at the beginning. We're not quite confident yet that the red curves are completely correct. It's a single precision. Yeah, it looks reasonable. Then what about double precision? So you should be able to push a little bit further in terms of convergency. Those numbers should be even lower than the single precision case. It's the case. Those black curves shows. So now we feel reasonable about the algorithm and the algorithm implementation. So, but that's only in terms of solving the object function. We don't know if the algorithm can do the inverse problem. So for this particular case, full data case, it has to, right? We know that. So we again use the model data in the object function and the full data. And you do it, and then because it's simulation study, we know the truth, that is used to generate the data, and so we can calculate the difference between the truth and the recount as a function of iteration numbers. That's what I'm showing here. It's single precision. In single precision case, it can go to say 10 to minus 7. It's pretty much the accuracy of computer, and we want to verify if it's really correct. Then we did a double precision, and sure, you push the accuracy to the double precision. So now we feel comfortable saying that the algorithm / implementation probably can solve the numerical problem, at least for the empirical verification study. We put it here. So just take a look at the image of the reconstruction data without truncation, data with truncation. They are full data in this case, offset, full angular range. And so in the middle, there are the reconstructions. Visually, you don't see that much difference, I can assure you, because the difference images in the right columns, it's with 10 to minus 5 display windows, 4 display windows. So anyway, so with that, we are in the position to look at the limited angle range problem or with the truncation data. Those are the sets of limited angle range configurations we look at. The first row is like single angular arc. And the second one is like you have two orthogonal to each other. And the reconstruction is from those guys. One is covering 150 degrees, 135, and 120 degrees. So this is just one example. For the single or for the limited angle range case, do you still, for this particular data set, like 120 degrees, can you solve the problem? Well, you can still solve the object function problem. If you have a one view, you can still solve it, but the object function problem is not quite right. In this case, the object function seems to be right. It's 10 to the minus 5, close to that, almost to the computer precision, single precision. So with that, I can show you a bunch of images. The first row is from data of the two orthogonal arc scans over total angular range, 150, 135, 120. And the second row is a single arc data. And if you look at of course, I'm not trying to beat up FDK. I'm just trying to give you a sense as to what if we use FDK, what it looks like. We are not saying FDK is the way to go. All right. So yeah, this is the profiles. Look through one of the lines through the image, and looks like you can push the limit to 120. Of course, some region is not going to be good. The lower parts can have some problem because the angular range is scanning that way. For the reason we for this particular object we set up the angle scanning angular range in in that way is that because people are mostly interested in the teeth, the bones there. They don't particularly care about what's happening in the in the back of the head. Anyway, so that's noiseless case, and so that sort of give you a sense that this approach may have a little bit chance to solve that kind of inverse problem under those conditions, limited angular range conditions. With that, then I would like to say, to a certain extent, the stability of the algorithm. So let's inject some inconsistency components like noise, scatter, or maybe a little motion, I don't know. So out of here, we inject a little bit noise, 10 to the minus 5, typical per ray, whatever. So this is a noise case. Definitely, the image quality is a little bit, somewhat worse than the ideal case, but it gives you a little bit sense. I'm not talking about application. I'm not talking about the product, not at all. Just say you have this approach, then if we add a little bit noise, see what happens. That's all. And the same thing for noise case, the profiles depends on the angular range, extent of energy range, and the scale of the angular range, the arrangement of the angular range. Anyway, so yeah, you can do a little bit, some kind of a summarized quantitative analysis like root mean square, PCC. One is like the measure the accuracy of the reconstruction. We use that already in the verification studies. I didn't tell you, but that's the one we used. And the second one is sort of give you some kind of a sense of the correlation, the visual correlation of two images. So if the first one should go to 0, the second one should go to 1. So this is the results for those cases between 120 and 150 angular range. So in this case, the two orthogonal arc give you the lowest root mean square, and they both limited angular range give you almost more or less the same PCC. And this is for noisy case. The trends are the same, but the magnitude is different, right? So this concludes this slides will conclude my talk. Not my talk, Dan's talk. I remember Emil saying, "Nice talk," So this is what we did. We look at this the inverse problem in the context of a limited angle range from offset detector. It's a combination of a limited angle range with some type of truncation data. Looks like there's some chance. So hopefully this kind of work will give us some kind of insights or information, whatever, to design whatever practically useful procedure down the road. Who knows? So thank you.
Questions?
Thank you very much for the nice talk. A question on so you really have very, very limited data. So anything that is perpendicular to your sampling trajectory is almost missing. So you kind of highly rely on the neighboring informations between different projections. So do you have requirement or guidance in terms of in certain angular range, what is the sampling that you have to?
That's a very, very good question. We don't have a sort of a detailed mathematical, analytical, whatever guidance, because I think it's going to be very difficult, very complicated because we're dealing with DD model. And also it has to be object dependent, the anatomy arrangement. Yes. So for this guy, basically I think the single arc case the arc is or my teeth. If you go from here, you can lose some kind of, it's not the best
Right.
trajectory. So in that sense, so there's some kind of qualitative sense, you can relatively easy to pick, but quantitatively, analytically, no.
I see. And another question is related to right now you chose to have one side truncation.
Yeah.
How about double truncation? It's limited angle anyways, so you
Yeah.
truncate it anyways. So which one is
Right.
better in terms of truncation?
Well,
anyway?
if you talk about inverse crunch study, ideal data, you have a very good chance to do, in that case, it's interior problem, a very good, chance to do interior problem. But
Mhm.
once you have a little bit inconsistency, it's very, very unstable. So that's why, but anyway, yes, we do look at those things a lot. I think it's really object dependent,
So in this
angle
case,
range dependent as
do you
well.
expect is a way that you're doing one side truncation is converging faster if you have the region of interest problem?
Uh-huh.
Yeah.
As I said, all the things we do here is the result at the point where the convergence has achieved, namely the object function has been solved.
Hmm.
Namely, so iteration number is not an issue here. So in that sense, I don't know how to answer the efficiency issue.
Mhm. Okay, yeah, thank you.
Xiaochuan?
Yeah.
Over here, I just asked questions. Can you go back? Can you go back
Yeah,
to the
to the
previous,
noise.
the non-noise reconstructions? Yeah,
Yeah.
go forward. The
Oh,
one that showed the images with no
Images,
noise.
okay.
And the reconstruction.
Very
That's
good.
one. Yeah, that one. So when I thought about this a little bit, if you have, offset detector and you have a small arc, it looks like the arc is above the teeth, right? In this picture.
yeah, the arc is like 150 degrees, 135.
Yeah,
120.
and it's in front of the
Yeah.
Yeah, okay.
right.
So when you think about the field of view in that case, I think there's going to be some part of the object which doesn't get any X-rays. There's some
Possible.
bits that don't feel anything. And it
Right.
looks like those wedges at the bottom
Yeah.
are probably what that is.
That's
That's
right,
the part
that's
which never got measured. It
Absolutely.
didn't feel a thing.
Absolutely.
But what surprised me is when you did the reconstruction with the noise,
That's
it
my
filled that in.
question.
So-
Oh yeah, we
So-
noticed that. I don't want to say that. Yeah, exactly.
so
we
can you say
noticed
something
that.
about that?
It's I don't know. It's just because in that case, you once you have noise, what are you solving? There's nothing. What you have is the summation of the model and noise. You cannot separate them. So basically, you are using a iterative process. You apply that to this combined thing. Whatever you get is whatever you get. Because you see what I mean? It's not like you only apply that to the model term. Now you have noise there, so they're together. Now you apply your algorithm that is only for the model part to this combined thing. I don't know what you're gonna get. Sometimes.
Okay. fair enough.
Yeah. Thank you.
No more questions on this?